Good morning, class. We are looking at chapter 2 limits. Here's 2.5 continuity. So we covered limits of sequences, limits of functions at infinity, limits of functions at finite numbers, limits algebraic methods, and now continuity. So again, recall, according to the definition, the limit of f of x as x approaches a is L. That's how we read this. The limit of a sub n as n approaches infinity is L. We say a sub n converges to L. If it's infinity, negative infinity, or dne does not exist, it diverges. To find limits, simply plug in. All of these cases, we are interested in finding the limit of f of x as x approaches a. And they all have the same answer, namely L, because in this case, left and right of a, we are in these two branches, the same thing here, the same thing here, and the limit doesn't change. However, the differences among those is that in this case, f of a equals L, which makes it continuous. In this case, f of a is b, which makes it discontinuous at a. And in this case, f of a is missing. But in all cases, the limit of f of x as x approaches a is the same, namely L. Horizontal asymptotes have a definition that the limit of f of x as x approaches either negative infinity or positive infinity is L. That means y equals L is the horizontal asymptote. The VA or vertical asymptotes, the limit of f of x as x approaches a, or a from the left or a from the right is either negative or positive infinity, gives rise to the equation of x equals a, being the VA or vertical asymptote. And the one-sided limit says the limit of f of x as x approaches a from the left and a from the right are identical, then the limit of f of x as x approaches a equals L. Otherwise, there is no limit. Now, 2.5 continuity. Definition: a function f is continuous at x equals a if, here's the definition of a continuity. Limit of f of x as x approaches a equals f of a. What does it mean? Number one, f of x exists. The output at a. Number two, the limit of f of x as x approaches a equals L. That exists. The limit as x approaches a is also there. Now, the two are identical. The limit of f of x as x approaches a and f of a, the limit is the same as the output. That is the definition of a continuity. A function is continuous over an interval I if it is continuous at each point a in I. If f is not continuous at x equals a, we say that f is discontinuous or has discontinuity at x equals a. Direct substitution property: a continuous function at a has the following limit value. The limit of f of x as x approaches a equals f of a, and functions with the direct substitution property are called continuous at a. Here's an example. At which numbers is f of x discontinuous and why? Just at a glance, at x equals 1, at x equals 3, at 5. So let's discuss each one. At a equals 1, I hope you recognize the limit exists. In fact, the limit is the y coordinate of this point, which is 1, but f of 1 is not defined. At a equals 3, what's going on here? The limit of f of x as x approaches 3 doesn't exist. Please understand the limit from the left is this one, -1. From the right is this one, +2. And f of 3 is this one, which is -1. It's known as continuous from the left, by the way. We say it's continuous from the left because we have a solid point here. So limit of f of x as x approaches 3 from the left is -1. From the right of 3, we are moving towards this point, which is +2. And then f of 3, because we have a solid point here, solid point, -1. And because these two are the same, first of all, this is not continuous at a equals 3. But because these two are the same, we say continuous from the left. We can say the function is continuous from the left at x equals 3. Also at number 5 is discontinuous. Why is that? Because the limit from both sides we end up here is not the same as the functional value. So the limit of f of x as x approaches 5 from the left, from the right, we seem to be moving towards this point. This seems to be 1. But f of a 5, the solid point, 1, 2, 3, seems to have a value 3. So this is equal to 3. They are not the same. So again, I want to make sure that we can read the graph easily. Example 2, g of x is defined as half of x plus 3 for x less than -2, x minus 1 for x larger than or equal to -2. Is g of x continuous at x equals -2, why or why not? First of all, I want you to know why we are interested at the end point -2, because I hope you recognize this one is a linear function, a line. Y equals half of x plus 3. This is a linear function, y equals x minus 1. And all polynomial functions are continuous from negative to positive infinity. But because it's a piecewise defined function, it has two pieces, we are interested at the endpoints. So we are going to look at three things. We are going to look at the function value and the left side and the right side limit. And the function value uses the equality. For the functional value, we use the equality part, which means we use this one. And we say g of -2 is x minus 1 such that x is -2. This is a notation. When we have different functions, we use this is red. This line segment is red such that. And so you plug in -2 and -1, they add up to -3. So the functional value is -3 as at x equals -2. Now the left side limit less than -2 uses the top piece. And we write the limit of g of x as x approaches -2 from the left. Please see this -2 from the left, like -2.1, for example. So you plug in -2 divided by 2 is -1 plus 3. And that gives us +2. The right side limit uses the bottom piece because we have the larger than here. And now the limit of g of x as x approaches -2 from the right, if you plug in, you get -2 minus 1, which is -3. Now, understand what happens here. The limit from the left and the limit from the right are different. So the limit does not exist. The limit of g of x as x approaches -2 from the left is not equal to the limit of g of x as x approaches -2 from the right. Therefore, the limit does not exist. Therefore, the function is discontinuous at x equals -2, or you say it's not continuous. However, notice the functional value and the right side limits are the same. Therefore, g of x is continuous at x equals -2 from the right. Okay, so to write this, you could write as follows. Okay, for this one, because the limit of g of x as x approaches -2 from the right equals g of -2 equals -3. So the terminology is the function continuous at -2? Absolutely not. But we say it's continuous at x equals -2 from the right. That's something to know. Types of discontinuity. Look at this one. We have a hole. Look at this one. We have a hole, and the function is defined at some point. So parts A and C are called removable discontinuities. Why is that? We could remove the discontinuity, in other words, fix the problem, by redefining f of x at just a single point 2. That's all you have to do. And it fixes the problem. So there's a hole. Whether the functional value is given or not, it makes no difference. You can fix it. And how do you fix it? Take a look at this one, and you factor as x minus 2 times x plus 1 over x minus 2. They cancel each other. You get x plus 1. Remember, y equals x plus 1 is this line, everybody. No hole. But this one says it's x plus 1 when x can't be 2. That means at 2, which means if you plug in 2, it gives you 3. This point has coordinates 2, 3, this hole, okay? Whereas this is defined as at x equal to be 1, so you have to redefine it as 3 to fix it, removal. So the function g of x equals x plus 1 is continuous because this is just a linear function. So the line with no hole, that's what it is. But these are the discontinuities as a result of being a rational function where they are not defined at x equals 2 in this case, and at this case at x equals 2 has a different value. Now, what's going on with these two cases? This one is infinite discontinuity, basically vertical asymptote. Whether it's defined at x equals 0 or not makes no difference. There's nothing you can fix. This one, there are infinitely many discontinuities. In this case, just a few. It's jump, and you can't fix a jump. Is h of x continuous at x equals 3, where h of x is x squared minus 9 over x minus 3 for x not equal to 3, and it's 7 at x equals 3? Well, we have to look at the limit, and we look at the functional value. The limit uses this function because, remember, as far as the limit is concerned, not at x equals 3. So let's take a limit of this one as x approaches 3. And I hope you recognize that if you plug in, you get 0/0, and the technique is factoring. So if you plug in, you get 0/0, and the technique is factoring. The numerator is x minus 3x plus 3. These two cancel each other. So we get the limit of x plus 3 as x approaches 3, and when we plug in, we get 6. So we have the limit. Is this equal to the functional value? Well, according to the given, the functional value is 7 at 3. So h of 3 is 7. Are they equal? No. Therefore, because the limit of h of x as x approaches 3 equals 6, not equal to h of 3 equals 7, h of x is discontinuous at x equals 3, or is not continuous. All right, we are going to evaluate this. When we plug in, we get 6 minus 6 plus 3, and this goes to 0. But we have 3 in the numerator. This is squared, 36, right? 6 squared is 36, minus 7 times 6, 42, plus 12. That's what we have. This is a typo, everybody. And so we get this one. The numerator is 3, the denominator 36 minus 42 plus 12, they add up to 6, and that's 1/2. So you plug in, it works out, you're done. In this case, if you plug in, you get 0/0, which is indeterminate. Because we have a complex fraction, the technique is LCD. The numerator has 2 fractions. The least common denominator is 3x. You're going to multiply and divide by it. And bear in mind, this is equal to 1. So you are going to multiply this by the numerator. You get x minus 3. And these two, you just write them as a product. Again, y. X is approaching 3, x minus 3 is 0, x minus 3 creates a problem. It is always the 0 in the denominator you want to get rid of. So you never distribute. So x minus 3 cancel out from the top and the bottom. You get 1/3x. When you plug in, you get 1/9. That's your final answer. Example 6, at what point/points is f of x discontinuous? Name the discontinuity. If removable, how would you redefine to remove it? So first, let's look at all discontinuities and then we name it. So start from left to right. As we look at this function, the very first discontinuity I see happens at -2. I move on. The next one happens at this point. Seems to be at negative 0.5. Okay. The next one happens here. Since it happens at 0. The next one happens here at x equals 1. The next one happens at 3, x equals 3. And the next one, I see a hole here, it happens at 5. So first, we write all of them, then we discuss them with details. So the type of discontinuity for each case. So I hope you notice that there is a hole here, but they're really connected. So if we could fix that hole, everything would be fine. So -2 is fixable, is removable. This one, again, we have the same situation. We can fix this at this number, -0.5. The rest we can't fix. Oh, over here, we can fix it also. At 5, we just see everything is fine. We just see a hole. So -2, this one, -0.5, this one, and +5, this one, removable. We can fix them by redefining it. But let's look at the rest of them, and then we come back to do the redefining. Notice right here at 0, there is a gap, so there is a jump. So there is a jump at 0. Over here, the same situation. I don't see any more jump. So we have 0, 1 as a jump. And there is one more, it's number 3. It's infinite, or VA, or vertical asymptote. So as far as the removable is concerned, let's look at each piece and see how we can fix it. Starting with the first one, at -2, we have a hole here. What is the limit? The limit is 2. If the limit is 2, if we redefine such that f of -2 is a 2, that fixes the problem. Same thing here. Notice that we have this way and this way, the limit exists, and the limit is equal to this number, seems to me is 3.5, but the functional value is 1. If we redefine it as 3.5 fixes the problem. Look at number 5. We're going this way from the left, we're going this way from the right, and we are moving towards this hole. It's undefined. So at 5, if we define it as 5, it fixes the problem. So f of -2, we define it as 2. F of -0.5, we define it as 3.5. And f of 5, we define it as 5. It fixes the problem. That's why they are called removable discontinuities.